Do you want to create the most amazing music videos with AI? Follow this tutorial to know more. Create amazing audio reactive videos with ComfyUI and AnimateDiff. Let's get started. To create this workflow of audio reactive music, install the following custom nodes in ComfyUI. All these nodes can be installed using the ComfyUI Manager. The models that you need are also listed here. Except for the next ones, the rest can be downloaded via the Manager. Dreamshaper, AnimateLCM, and the AnimateLCM LoRa can be downloaded from Civit.ai and Hugging Face. The audio reactive nodes have been developed by SaltAI. SaltAI is a tool that allows you to develop ComfyUI workflows for free. You can deploy the workflows in Discord and have an image or video generation bot. It's like having your own tailored Midjourney Discord, but with ComfyUI workflows. If you want to play around, I leave the link of my Discord with some examples of what can be done. Search for it in the Manager and install it. It is the last SaltAI audio viz. When you have all custom nodes and models installed, restart ComfyUI. This workflow is fun and interesting, but it is not an easy one. However, I invite you to keep watching and learn about how to create amazing generative AI videos in ComfyUI. Before you start working in the workflow, you need to have a music clip prepared. You can use free software like Audacity or any other online tool for the job. I have been able to run up 1-minute music clips, but try first with shorter. The longer the animation, the more VRAM and CPU requirements. Use a BPM analyzer to find out how many beats per minute the song has. You will use this number later to synchronize the image transitions. In ComfyUI, start by adding a video upload node. For this example, we use a video mask to create a moving circles grid. I leave a link in the description with this mask. The original video is 16 frames per second. To slow down the mask, we will force the video to run at 32 frames per second. Add now the audio load node from SaltAI. We use it to load the audio clip. Write the path of the audio clip in the path field of the node. Make sure to have a / sign at the beginning of the path. Set the frame rate to 16. The number of BPMs of this clip is 125. We use this number in the manual BPM field. To start testing the workflow, set for the moment a duration of 4 seconds, which will be about 8 beats. We want to create 3 layers with different images, which react to the music and follow the pattern of the reference video. The separation between masks is going to be defined by the frequencies at 200 Hz and 3000 Hz. For each of the layers, we want that the images change according to the frequency here shown. Add a frequency cutoff node which will create the first separation for the low frequencies. With this cutoff, we want that the masks move along the beats of the drums and the bass. Duplicate the node and use it as high-pass filter at 3000. With this cutoff, the mask will dance with higher frequency sounds like synths and hi-hat. The mask for the low-pass filter is created using the audio frame sync schedule node. We also copy the node and do the same for the high-pass. These nodes create a schedule with the intensity of the sounds according to the filter frequencies. Right-click over the sync node and convert the frame rate to input. Do it also for the high-pass audio frame sync node. Now, connect the frame rate output of the audio load node to the sync nodes. Convert also the end frames to input. Connect the total frame count of the audio load node to this new input connection. With this, we indicate the node to stop the synchronization when the audio finishes. Add a scheduled binary comparison node for each of the branches. This node creates a black and white mask from the reference video frames, based in the schedules created in the audio frame sync node. We are going to connect the reference video to these nodes. but the video duration is less than 2 seconds. So we use a repeat image batch node to repeat twice. This is enough for this test, but later we will need to increase the number of repetitions. Connect preview animation nodes for each of the masks to see how it looks like. When developing workflows, try to build small pieces and use pre-visualizations to check that the results are as you expect. Remember to use a frame rate of 16. When ready, run the workflow. The workflow works, but the masks do not look like what we want. The epsilon option in the binary comparison node was active. Deactivate it. Change also the amp controls. These control how sensitive the mask reacts to the audio. For the first mask, use for example an offset of 0.2 and a control of 0.5. For the second, use an offset of 0.2 and a control of 0.4. You can change and test different values to see what looks better to you. Now looks better, but it seems that the mask stops moving. The reason is that the total amount of frames is longer than the audio clip. This has an easy fix. We just need to match the amount of frames of the audio and the video. Add a get range from image batch. Convert the number of frames to input and connect it to the frame count output of the load audio node. Connect now the output of the repeat batch node, and this to the scheduled binary comparison nodes. Fine-tune now the amp control and offset of both audio sync controls. The offset defines the initial size of the mask. The amp control how the mask grows with the change of the beat. Play with these parameters until you find what works for you. We want the high frequencies to control the inner layer, so we will invert the first image. We use the lower frequency for the outer layer and the background. We also add an invert image node to create the background layer. To see how the three layers combine, we first convert them into color using the mix color by mask mode. Connect the image output to both mask and image inputs. With the R, B, and G parameters, we can define the color. The inner mask will be yellow, the outer layer green, and the background blue. Use preview animation nodes to visualize better how they look like. Let's blend the images to see how overlaying the three layers looks like. Use the image blend node, or any other node that combines images one over the other. Use screen and a blend factor of 1. With the screen mode, the black color does not mix in the images. However, the colored parts of the image will combine. Therefore, if some of the masks overlap, you will see a color which is not blue, green, or yellow. The addition of the masks creates a white circle, which is an overlap of the masks. If you want to have the overlap, it is fine to keep it and use this setup. However, for this tutorial, let's see how we can make a better fit of the layers by using composite masks. First, we convert the images into masks. Use the Convert Image to Mask node. Do it for the three layers. Add a mask composite node. Connect the inner mask to the destination and the outer mask layer to the source input. Use the multiply option. With this option, a new mask is created when the green and yellow masks overlap. This way, we make sure the smallest inner circle is isolated. Duplicate the mask composite node. Connect the mask of the green layer and connect it to the destination. The yellow image mask will be now the source. But now choose Subtract as option. What we do with this is to create a ring which corresponds to green circle area that does not overlap with the yellow mask. To make sure this new ring does not overlap with the new inner circle, we duplicate the mask composite with the subtract operation, and connect both. Now that we have the masks, we can convert them again into images. I hope you do not get dizzy with all the blinking. We can reuse the image by mask configuration to redo the colored composition. Disconnect the starting mask images and reconnect them with the new composite image masks. Well, the resulting workflow looks messy, but as you see, the composite of images does not show any white stripe, as it was the case before. Let's tidy up a little bit the noodles before continuing. This is an example of what can be done with masks. Of course, you can change how you want to construct your masks to have different effects. It is up to you and how creative you are to make the most amazing animations with ComfyUI. The next step is to create the different images that are going to be changing in each of the mask layers. We need to do some math to know how many images we want to create. Depending on the duration of the audio clip, the BPMs, and how often we want the images to change, the total number of images will be different. In this case, we want that the different layers change at a different rhythm, resulting also in different number of prompts per layer. Replace the text clip encodes of the default workflow by the batch prompt schedule node. In the text field, we define for each frame the prompt. This is done by creating a list of individual prompts. We need in total 17 images, but see that the index of the first image is 0. Therefore, the last index should be 16. Check that the prompts are separated by commas. You do not need a comma in the last one though. Start writing a prompt for each of the images. Do it according to the layers and the results you want to create. The longer the audio and the more frequent changes you want, the more prompts you will need to write. LLM nodes can help you with that, but I think this workflow is complex enough to explain how to use them here. We will do it in a different occasion. For repetitive concepts, you can use a pretext and a append text. This way, you do not need to write down for all the prompts the same, and save some time. For example, if you want them to be all 4K, share a similar style, have same negatives, etc. We define the maximum number of prompts to 17, which is the number of images we want to create. In the case sampler, we change the parameters as we wish. In this case, we will use a CFG of 5. The sampler is DPMPPSD and the scheduler Keras. We will use a grid node to show the images nicely. It is not critical for the workflow, but helps in visualization. Finally, type 17 in the batch size of the empty latent, and run the workflow again. Good, a nice set of images have been created. Play now with the prompts, the seed and the parameters of the K-sampler to fine-tune the images you want to use for the music video. When you are happy with the results, you can now continue. We are going to separate the images created, and group them for each of the mask layers created before. Add an image from batch node for each layer, so a total of 3. Change now, per each image from batch node, what is the start index? Remember that the first image has the index 0. For the moment, select only one image per layer to test the workflow. You will change the length later. These images are going to be used in 3 IP adapters. Because we are alternating images, we will need to repeat each image as many times as the number of frames for each segment defined by the beats. Use the image expand batch and connect it to each of the image from batch nodes. Convert the size of the nodes as input, so we can connect it to the frame count of the load audio node. The total amount of frames for the expansion is defined by the frame count in the load audio node. This node is far away, so to keep it cleaner we will use a set and get node. And now add the get node of the frame count, and connect it to the size input of the nodes. Add a prepare image for clip vision node for each mask. Depending on the image and what you want to achieve, use center or pad. Try different options and compare results. Normal IP adapters use images of 224 by 224 pixels. If you want more resolution, you need to use the tiled IP adapter. Place in the workflow 3 IP adapter advanced batch nodes. 1 for each mask and series of images. The images can easily be connected from the prepare image for clip vision nodes. The new IP adapter also allows you to connect a negative image, but we will not use them in this example. The masks are a little bit far away. Of course, you can connect them directly, but for this video I will use the set and get nodes, so the workflow is a little bit more clear. For complex workflows, I like to use set and get nodes because give clarity to me. But if you think for these videos direct connections are better to understand, let me know in the comments. Connect now the masks to each of the IP adapters. Make sure that the masks connect to the right IP adapter corresponding with the images you want to use for each layer. You can use preview nodes for the images to make sure which image series correspond to each mask. To connect the checkpoint to the IP adapter, we will also use set and get nodes. They are my favorites, sorry. You should know, though, that for some data types they do not work well. Connect the first IP adapter to the IP adapter unified loader. I suggest you to use VIDG, but feel free to use others. Connect the models consecutively for each IP adapter. Remember also that the checkpoint model needs to be connected to the unified loader, and that the IP adapter model needs to be connected in each node. Otherwise there will be an error when you run the workflow. If you encounter difficulties to match the IP adapter and clip vision models, I suggest you read the documentation from the IP adapter GitHub or check the videos of Latent Vision. Adjust the strength in each IP adapter. We will use 1.5, but other IP adapter models may work better with a different weight. We start now creating the animation part of the workflow. We will use the clip from the starting checkpoint. Place a get node with the clip close to the last IP adapter. Connect the clip to a 2 text encode nodes. These are the regular positive and negative prompts. However, you do not need to fill them for this workflow because the IP adapter does most of the work. Connect now an advanced controlnet apply node. We are going to use the composite mask we have created to create line art lines. With linear, we will create a more clear differentiation between the images of the different layers in the final animation. However, this step is optional. And you can also use other controlnets, such as QR Monster, that work also nicely. Anyway, in this example add a load advanced controlnet model, choose lineart, and connect it to the controlnet apply node. Use the realistic linear preprocessor and connect it to the composite image with the yellow, green and blue masks. This preprocessor creates 2 circumferences, corresponding to the borders of the masks. Set the strength of the controlnet to 0.5. Add a case sampler node. This will sample the final animation. After the last IP adapter, add a LoRa model only loader. Select the Animate LCM T2V model. Connect it to a UseEvolve sampling node. Now, continue connecting it to an Apply AnimateDiff model simple node, and this to an AnimateDiff model loader. Select the Animate LCM T2V model. Add context options. For this workflow, use the standard uniform node. No need to change the settings. Connect the output to the case sampler. If you want, use a multival dynamic node connected to the scale multival. I use it with a value of 1.25. Connect also the positive and conditioning outputs of the controlnet to the case sampler. Next, add your empty latent image. The resolution will be 768 by 512. Convert the batch size to input. Connect now the frame count to the size batch input. Like before, we will use a get node to use this variable. Adjust now the settings of the case sampler. Use any fixed seed you want. Change the number of steps to 10. Decrease the CFG to 1. Any value between 1 and 2 is OK for LCM. select LCM as a sampler. Use SGM uniform as scheduler, and keep denoise at 1. Connect your case sampler to a VAE decode node. We are using the VAE from the original checkpoint loader. However, you can use other SD 1.5 VAE using a VAE loader. Do not use VAE from SDXL checkpoints. Finally, use a video combine node to render the animation. Set the frame rate to 16. Use the MP4 codec and deactivate the Save Output option. Finally, run the workflow. With this first visualization, we can adjust some parameters. For example, we are going to reduce the strength of the LoRa adapter to 0.85. Of course, you can fine-tune other settings. The image seems more clear now. Let's continue. First, we need to add the original audio to our video. You can use a video editor, if you want, but we will use the Audio to VHS audio node. This node converts the audio format to the one suitable for the video combine node. Increase the duration of the clip to 16 seconds, which is what we want to animate in this example. You can now select all the images for each layer. Increase the length of each image from batch node, according to the predefined number estimated in the calculations. Increase also the number of repetitions of the video. We will use 9 repetitions. The calculation here is incorrect because we only do 16 seconds. In this case, it does not matter because we later shorten the number of frames. However, to avoid these mistakes, it is convenient to automate some calculations. This can be done using math nodes, but we will not cover them today. When you are done refining the settings of the workflow, you can further upscale and use frame interpolation for nicer animations. A simple upscale will consist of using an image upscale with real ESR-GON X2. Higher resolutions with an X4 upscale is possible, but consider the limitations of your machine. The upscale with model batch node will help you when the amount of frames to process is high. But if it is too much, ComfyUI may kill the process. Finally, Rife video frame interpolation will help you in obtaining a smoother animation. Reduce the cache size to avoid the system crashes. Remember to double the frame rate if you are doubling the number of frames. And if everything works, you can now enjoy an amazing audio-reactive music video. That's all for today. I hope you have liked this video. Check out my other videos and subscribe.